idea is, I think, that we rotate the roles every week, but you keep the same season. So hopefully everybody at your pod is a different season, and if not, you should tell your TA. And you can get you don't have to switch pod numbers, but you can switch season number pretty easily. And I think that next week, the plan is falls will be theorist, lead theorist. I've sent out a little theory video. Winters will be the experimentalist. Springs will be the managers. And summer will be the archivist, filling in the term booklet. And it's this flying pig. Okay. Just a little curious as to what people said to that. So there are a few people that are kind of in the dark about this whole system. Only one. Okay. That's good to know. Okay. Anyway, let's go. So I wanted to actually go through some stuff I didn't quite get to on Wednesday, but it's all Chapter 5 stuff, circular motion. That's exactly what we're doing next week. The flying pig goes in a circle, and this is uniform circular motion mostly. But part of this, the tension is what you have to actually determine when you're doing that lab, because tension is one of these as-needed forces. Remember, normal force, tension, and static friction are all self-adjusting. And so you have to actually solve out Newton's second law to find these. And that's exactly what you're doing with the flying pig. There's an acceleration that you know in different directions, and you can find the tension. Normal force is just, like right now, there's a normal force on my feet from the table, which is whatever is needed to keep me from crashing through the table and falling down. Tension is whatever is needed to keep the string from breaking, I guess. And static friction is whatever is needed to keep an object from slipping on a different surface. So you got to draw a force diagram, define your axes, and then your positive axes, you add all the forces in the plus direction, you subtract all the forces in the negative direction, and they should all balance out to give you mass times acceleration, where mass is the mass of the object you're doing the force diagram for. So I want to try it here. Here's a car, and it's rolling over the top of a hill at some speed, v. And there's the velocity vector shown there, which right now is directly towards the right. So presumably there's normal force, n, which is the surface acting on the car. There's also gravity force from the Earth acting on the car, and those are in opposite directions here. But those are the forces acting on this object. They should sum up to be the mass of the object times the acceleration of the object. That's Newton's second law. So in this case, how does the normal force compare to the gravity force? Greater than, less than, equal to, or you have to know more about V to answer this question. Please think about that. Maybe pair up. It's a little more sparse in here. You may have to reseat yourself, but it's really good to have a neighbor. Ooh, sort of all over the place. Let's actually look at percentages. There you go, 55%. So that's what I liked. Basic idea, try to draw this out, is that so what I would do is say that you define, if this is like a big circular path or something like that, define plus r is down. The reason it's down is because r always points towards the center of the circular path. Okay? And so the way Newton's second law looks is the sum of F sub r is equal to the mass times the acceleration in the r direction. So it's going to be F g is plus, because that's in the plus direction. Normal force is negative because that's in the negative r direction, equals m times v squared over r. Okay? And so you can kind of solve out for normal force here. If you add to both sides, you get the normal force is Fg minus the mv squared over r. And I've set this, I like to set it up so that all of the variables in my equation are positive numbers. And then I can just tell if there's a plus in front of it, it's positive. If there's a minus in front of it, it's negative. So I'm taking normal forces mg, the force of gravity, minus something positive. Okay. And you can even imagine it going to 0. If you go fast enough, you might fly off the hill or something like that, right? Okay, so next question. What if you're in a valley? Let me think about that. Okay, want to check this one? Let's go through this one. Yeah, you guys are getting it. It's more in this case, so why? Let's go through this reasoning again. Same sort of thing. This is part of a circular path. So you got to draw, imagine a circle. The center of the circle is up here, so you define plus r as being towards the center of the circle. That's key. You can't solve Newton's second law until you've defined, A, define your system, which is the car in this case, B, define your coordinate system. Set up your axes. Those are the first two steps of solving these problems if you want to get normal force. So I've done that, and now, again, Newton's law just looks like this, r direction, mass times acceleration, the r direction. So the sum of all the forces, you got normal is now a positive force because it's towards the plus r direction. Gravity is now a negative force, mg, because it's in the negative r direction. This equals mass times v squared over r. And so normal is going to be Fg plus mv squared over r. It's going to be a little bigger now. Okay. Again, setting up all my terms to be positive numbers, and the plus or minus is going to show the direction. Okay. Okay. Good job. Alrighty. Let's do actually an banked curve example. That's another thing I was planning to do on Wednesday. These come up all the time, and there's a whole bunch of these on your problem set 4, which I've posted. Problem set 4 is actually not due this Sunday. It's due next Sunday, so you'll have lots of time to work on it during practicals next week as well, if you have any questions or something. But you should get going on it. We're almost done chapter 5 actually now, so okay, bank curve. A highway curve of radius 70 meters. So the idea is that the top view is showing that this curve is part of a circular path of radius 70 meters. But then there's a banking angle, so if you view the car from behind, you see that the road is tilted. So you really need to draw two perspectives on this, top view and rear view. You have a constant speed v, so this is uniform circular motion, v0. It's a circular path, as viewed from above. So a sub r is equal to v0 squared divided by r. And it says without assistance from friction. So without friction, we actually don't have Fs. And remember, static friction is a self-adjusting force. We don't know what it is, but actually we're told in this case that it's 0. And that's okay. So first step, define system. Is the car. And second step is draw a force diagram and then define your axes. So this is going to be your force diagram. We already have a kind of a sketch over here. The question is, should I do the force diagram from the top view or the rear view? So I don't think the top view is going to be that helpful because you need this angle. That's going to be key here. So what I'm going to do is I'm going to use the rear view for the force diagram. It's the only way this is going to work. So here you've got the car. The normal force goes up like this, normal. And the gravity goes down like this. So this is like the normal of the surface on the car. And this is the force of gravity of the earth on the car. And don't forget there's a road in there. The road is perpendicular to the normal force, but there's no friction, so in fact that's all the forces. And we know, by the way, that it's accelerating in this direction because the center of the circular path is now to the left on this rear view diagram. So what we want to do, remember second step, once you define your system, define your axes. So I'm going to define plus y to be up and plus r to be to the left. And the reason it's to the left is because that's the direction towards the center of the circle in this rear view. And that's pretty much, these are the trickiest parts of this problem. I've pretty much done all the really, really hard work now. And now, it's just setting up the math. You're just going to put some of the forces in the y direction as mass times ay, which is 0. Some of the forces in the r direction as mass times ar, which is m, which is v squared over r. And we're done. So don't forget that, we have to actually do this normal force as a diagonal. So remember, normal goes like this. And that is, so what we want to get here is there'll be n in the y direction and n in the r direction. Here's a right angle there. This is a right angle. Trying to figure out how to solve this here. I think that if you look at all these angles, this is 90 minus theta. And so I think this is theta. And then by the x rule, this is theta over here. I always have such trouble with all these thetas, but it looks like this. Here's nr, which is positive, and here's ny, which is also positive, I think, and then here's n. Then I think that nr is going to be n times sine theta, because theta is down here. This is another tricky part, actually, is figuring out which one's sine, which one's cos. And ny is n cos theta, where theta is the banking angle. And a sub y is 0, right? All right, so then next step is I'm going to represent mathematically. That just means setting up your Newton's laws. So let's make a little table, actually, where I've got, what do we have? We have the r component, and we have the y component. So ways of doing this, and we have the normal force, and we have the force of gravity. So in the gravity is easy, right? There's no r component to it. There's just negative mg, because it's in the minus y direction. And I like m and g to be positive numbers, so that's my negative. And then the r component of normal force is n sine theta, y component of normal force is n cos theta. And then we can just sort of add these things up. So a sub y is equal to 0. That means the sum of all the forces in the y direction is equal to 0. And that's going to be just add these up. N cos theta minus mg. That equals 0. And what that means is that n is equal to the mass of the car times g divided by cosine of theta. And as usual, the normal force is not easy to determine. It's you have to balance some forces. It's self-adjusting. And then the r direction, a sub r, is, again, a sub r, I guess, is equal to the sum of all the forces in the r direction divided by the mass of the car. So it's going to be n sine theta. I think that's the only contribution there, divided by the mass. And we can take n from what we just computed over there, and we get mg over cos theta times sine theta is on the top, and there's another m on the bottom. Actually, there's m's on the top and the bottom, so that's lucky. That means I can cancel this m with this m. And you get that a sub r is equal to g times sine theta divided by cos theta. And that's equal to v squared over r, because in a v0 squared over r. So solve for v0. That's it. So v0 squared is equal to g times r times sine theta divided by cosine theta. So v0 is equal to the square root of all that stuff. G times r times sine theta divided by cos theta. So it's equal to 9.8 times 70 meters times sine of 15 degrees divided by cosine of 15 degrees. So I got 13.56 meters per second. So it's around, I guess, 2 significant digits, 14 meters per second. So if you go at that exact speed, then the static friction is 0. Because all the centripetal, I guess, radial acceleration or radial force is provided by some component of the normal force. So even if the track was perfectly slippery and made of ice, the car would still stay on the track as long as it traveled at exactly 15 meters per second, 14 meters per second. Okay. How are you guys doing? Any questions on that? Some of these things you just got to kind of get used to it. Like I said, there's lots of practice problems on the problem set for you to try this out yourself. I've often said you don't learn to play sports by watching people play sports. You learn by playing, and so it's the same with physics. You don't learn physics by just watching me solve problems. You gotta do it. Yep.
I just have a question.
Yep.
For the step where we're simplifying, can we just take sine theta over cos theta and simplify as tan theta?
Yeah, absolutely. Yeah, yeah, for sure. That's even faster. One less step. 10, 15. You should get the same answer, I think. There's always more than one way to do it. That's another thing. And so you're going to have your own style. That's sort of why it's good. You need to, every one of you needs to figure out how to solve these problems in your own way that works, and that's going to work on the term test when you're all by yourself. Okay, so this morning's pre-class quiz, 2 objects attract each other gravitationally. If the mass of each object doubles, how does the magnitude of the gravitational force they exert on each other? So you're going to see this equation coming up. G is some universal constant, m1, m2, divided by the distance between the centers squared. So if you double m, you double m1 and double m2, I think the whole force is going to go up by a factor of 4 on both of them. Did pretty well on that. A hypothetical planet has a mass 1/3 of and a radius 3 times the Earth. What is the acceleration due to gravity? We're going to talk a little bit about that, but the acceleration is going to be the force of gravity divided by the mass of the acceleration of 1 or something like that. So it's just going to be g times m2, something like that, divided by r squared. So if you the mass is 1/3, that's going to be 1/3. If there are 3 on the bottom squared, that's 9. 3 times 9 is 27th, I guess. And then this satellite. Why does a satellite in a circular orbit travel at a constant speed? So the gravitational, let's look at the wrong answers. The gravitational force exerted on the satellite is balanced by the centrifugal force exerted on the satellite. So we don't use centrifugal force in this course. It's not a real force. It's a fictional force, I guess, that you would have if you were in an accelerating frame. So C, there's a force exerted opposite to the direction of motion of the satellite. Well, that would slow it down, I guess. Some of the forces exerted on the satellite is 0. Well, then it wouldn't go in a circular path at all. It would go in a constant velocity, a straight line. So the only one left is there's no component of the force exerted along the direction of motion of the satellite. So all the force is radial, and there's no tangential component. That's the idea. Uniform circular motion has no component of force along the direction of motion. There were a couple of nice questions from the pre-class survey. Someone asked, I'm confused about how radial acceleration can be both positively and negatively correlated with radius, v squared over r. And it also is 4 pi squared over t times r. So which is it? Does radial acceleration go down as you increase the radius, or does it go up? Well, answer is, it all depends on what you keep fixed. So there's two equations for acceleration. I think it looks like this. A sub r equals v squared over r. Or a sub r is equal to, I think it's 4 pi squared over t squared times r. So if you hold the speed fixed, then radial acceleration goes down as r goes up. So meaning that, like if you are in a car, some fixed speed, you're going 50 kilometers an hour or something like that, if you go around a hairpin turn, that takes a lot of acceleration as opposed to going around a gradual turn. Okay. Or if you hold the period fixed, such as if you're on one of these merry-go-round or a little turntable or something, your speed now is not fixed. Right? People at the edge of the merry-go-round are going a lot faster, and someone who's right at the center will be going no speed at all, right? V is 0 at the center. So in this case now, your acceleration is greater as you increase r. So the kids at the outside of the merry-go-round have to hang on the most to stay on there. So I'm glad you guys are thinking about this stuff. What else was there? So yeah, this is just an interesting one, is that if you look at Cartesian coordinates or something like that, y and x for uniform circular motion, then what's happening is Vx and Vy are continuously changing. Okay. And also Ax and Ay are continuously changing. But I think the sum of the squares and the square root of that, those are constant numbers, constant speed. So the components are always changing, but the speed itself is fixed. Okay. I think sine squared plus cos squared is 1, and that's what saves our lives here. Okay. Why did the physics book look so sad? Because it had too many problems. Right. And also, and there's a turntable with a chipmunk on it. So that's happy birthday to Zoe. I'm not sure which Zoe's birthday it is, but happy birthday. Okay, so there's this story that Isaac Newton, long ago, came up with Newton's laws. Newton's first law being that if there's no force on an object, it moves in a constant velocity in a straight line. And it takes a force to accelerate something, say, in a circular path. So it was known at that time that the moon orbits the Earth. People spent a lot of time looking at the sky back then. The moon orbits the Earth once every month. That's why it goes through all these phases. So Newton was wondering what force could it be that would pull on the moon towards the Earth that would keep it on a circular path. Because really, if there's no force on the moon because it's out there in space, it should just go in a constant velocity in a straight line and leave the Earth. But it doesn't. It seems to be attracted to the Earth. And so he's thinking about that. Why doesn't the moon fly off in a straight line at a constant velocity? And then an apple fell and hit him on the head. And then he thought, well, maybe, so that apple just got pulled towards the center of the Earth. Maybe it's that same force reaching way out into the heavens and pulling the moon. And that's correct. So Newton came up with this universal theory of gravity, which is that gravity is an attractive, long-range force between any two objects. So meaning that right now I'm attracted to that table over there, and the table is attracted to me, but it's pretty small. There's when two objects have masses m1 and m2, and the centers are separated by a distance r, each object attracts the other with a force given by Newton's law of gravity, where capital G now is a universal constant, 6.67 times 10 to the minus 11 newtons times meter squared per kilogram squared. And it's an equal and opposite force on both because it's the same interaction. That's Newton's third law. But this interaction force on both those objects is the magnitude is given by this equation, gmm over r squared. And you can measure this stuff. There you have these two lead balls. This is an experiment on the second floor of MP. And you can measure a force. There's two smaller little masses that are hanging from a torsion cable, and there's a little laser which reflects off a little mirror which is attached to the torsion cable, and as it swings back and forth and you adjust the positions of these lead masses, you can measure this attraction and find this 6.67 times 10 to the minus 11 by finding the gravitational attraction between these masses. But you kind of have to be really calm. Like if someone opens the door and says, "Hey, how's it going in there?" Then the wind currents will blow the little lead balls, and you'll like yell at the person, "Ah, get out of my room. I'm trying to measure G. I've been spending 2 weeks on doing this thing." That's happened to me. Okay, so let's do an example. You have two objects. Object O with a mass MO sits at the surface of a giant spherical rock, which is floating in space. So you have to imagine two objects floating in space. The giant rock, we'll call this object E, maybe. Let's come up with a letter here. Has a mass 6 times 10 to the 24 kilograms and a radius of 6,400 kilometers. First of all, what's the force of gravity of E on O? And question B is, can you think of a name for object E? You can name it anything you want, I guess, but let's write this down. R is 6,400 kilometers. What do I have here? R is the distance between the centers of the objects. That's key to figuring this stuff out. The centers of the two objects. One's very large, and one is very small. So I think here's the center of E, here's the center of O, so this distance is approximately going to be just the radius of E. I think it's going to be the 6,400. 6,400 times 10 to the 3 meters. Don't forget to convert things to SI units, I think, in this course. Otherwise, you're going to be off by a factor of 1,000. So, I don't know, the system. Let's define the system as MO. Okay? So the force, there's only one force here. The force of E on O. I just gave away. So it's just F is equal to G times the mass of O times the mass of E divided by R squared. So F is equal to 6.67 times 10 to the minus 11 times whatever MO is, wasn't specified, times 6 times 10 to the 24 kilograms is the mass of ME, and divided by 6,400 times 10 to the 3 squared. If we do all that, you get 9.8. Okay. F. Newtons. Okay. And does anyone have an idea for a suggested name for this rock in space? Starts with the letter E. Earth. I agree. If you have a giant rock in space of this radius and this mass, you could call it Earth, and it would be our dear home planet. So. And then, if you had a kilogram object on that Earth, there would be a gravitational force. So the idea is, yeah, I'm attracted to that table over there. I'm also attracted to you and the wall, and also all the dirt below me and Mount Everest and everything. And if you add up the force of me being attracted to every other kilogram of these 10 to the 24 kilograms of the Earth around me, the vector sum adds up to being pulled straight down towards the center of all that mass. And actually, that's a difficult problem to solve. You need calculus. And so that was actually the first step that Isaac Newton had to do when he had this theory, is invent calculus. And once you do that, you can solve it, and you get that the sum of all those forces is straight down, and it works. So if you don't have enough math, just invent more math. That's the moral of the story. So gravity for Earthlings looks like this. If you happen to live on the surface of a large planet with radius r and mass me, then you can write this whole GME/MO over r squared. You can do a short form where you define lowercase g to equal uppercase G times the mass of your planet divided by the radius of your planet squared. And for us, that's about 9.8. I actually get 9.83. But I guess maybe it depends on your altitude exactly. We always use 9.80 on this course. So. There might be little effects, like maybe there's the rotation of the Earth might have changed the effect of gravity a bit, and height or something like that, altitude. So, but it's basically 9.8 is the main thing. Okay, what time is it? Over. Okay, next thing is, the Earth is curved. So the idea is that if you were to go 8 kilometers in that exact direction, then the curvature of the Earth would drop by 5 meters. And so there's an interesting thing you can do, is that if you launch a ball horizontally, so the y component of the velocity is 0, how far does it fall in 1 second? Well, it turns out, I guess you can do d is equal to 1/2 gt squared. That's equal to 4.9 meters. So what's kind of interesting is that if you were going 8,000 meters per second, then if you went 8,000 meters, you would fall 5 meters. But the Earth would have curved 5 meters, so it's 5 meters farther down. So actually, you wouldn't be any farther away from the surface of the Earth than when you started. And it would just keep going. So that'd be an orbit. So that's one way of thinking of what an orbit is. And another way of looking at this is, and this is something Isaac Newton drew in his Principia, is that if you have a cannon, so this is not to scale, but a cannon that's sitting up on top of a mountain, and you shoot it out at some speed, it'll fall down and hit the ground. But if you went faster, if you increase that initial speed to b, it would go farther. If you increase it to c, it would go all the way around and hit you in the back of the head. Okay? Because gravity pulls you towards the center of the Earth, and that's not a fixed direction. So let's talk about the space station. There is a Chinese space station in low Earth orbit called Tiangong. Orbital altitude is 380 kilometers. This is the crew that's currently up there. They're going at 7.68 kilometers per second. So it means they go the entire distance around the Earth in about 92 minutes. China Manned Space Agency, CMSA. These guys went up there in the summer. Those are their names. So you can actually figure out the radial acceleration by using v squared over r. So v is equal to 7.68 kilometers per second, so don't forget to times by 10 to the 3 squared to get meters per second. And then divide by the radius, which is, if you look at they're 380 kilometers above the surface of the Earth, but don't forget the radius of the Earth, so you get 6,750 times 10 to the 3 meters. If you divide that all out, you get that their radial acceleration is 8.7 meters per second squared. Okay, radial acceleration. So which direction is radial acceleration? It's towards the center of the circular path. So my question for you, I guess, let's do a couple of questions. This is one of the astronauts that's on the on Tiangong, Professor Gui Haichao. And assuming that Gui has not changed his mass since he moved to space in the summer, what is the force of gravity of Earth on Gui? Is it A, exactly 0, B, exactly the same as the force of gravity was when he still lived on Earth, C, almost the same as the force of gravity on him while he was on Earth, but a bit less, D, not exactly 0, but much, much less than the force of gravity on him while he was on Earth? And they're playing water ping pong, I think, here, actually, in this. They're making cool videos while they're up there. Once you've thought about that, please share with your neighbor. Make sure you're voting the same way as your neighbor. So it's sort of split. It's either 0. So 0 is a good guess because they're playing ping pong with and it looks pretty weightless on the videos, but it's not correct. And let's think about it this way. Oops. Send to all. You are right now some distance from the center of the Earth. I guess it's 6,400 kilometers. You're not at the center, right? Astronaut Gui Haichao is currently living on the Tiangong space station, which orbits at 380 kilometers above the surface of the Earth. So if you think about that, where the G comes from, it's your distance from the center of the big planet, right? So I think it matters how much farther is Gui from the surface of from the center of the Earth than you are right now. Just give you a minute to click in on that. And then we'll get to the million-dollar question here. Oops. I thought I was showing the other screen. Okay. Yeah, it's fine. That was supposed to be secret. Yeah, so idea being, the answer that I'd like to hear was A. Sorry about that. I am running a little short on time. So, okay, million-dollar question. Let's answer this one, which is, the Tiangong space station is accelerating towards the Earth at 8.7 meters per second squared. So that's that radial acceleration that I was talking about. So why doesn't it crash into the Earth? So let's launch this on Top Hat, and I'll give you some time to think about. I think that 3 of these answers are dead wrong, and one of them is what I like, what I like to see. So and we'll put it on laptop 1 now. A, bad question. It's not actually accelerating at 8.7 meters per second squared towards the Earth. B, because as it accelerates towards the Earth, it also moves in a sideways direction, so it misses the Earth. C, this acceleration is compensated for by rocket blasters, which continuously point away from the Earth. Or D, 8.7 meters per second squared is not a noticeable acceleration. It would take millions of years to travel 380 kilometers in a straight line at that acceleration. Like I say, 3 of those are dead wrong. So pick your favorite. Okay. Well, that's very nice. That's exactly what I was thinking as well. So that's what an orbit, I guess, is you're kind of always missing, right? It's falling with style or something. So I liked this. It's certainly true that the radial acceleration is 8.7. There's no rocket blasters needed for an orbit. Once you get up there, you turn off all the engines and you're just floating. And I think if you were in an elevator that was accelerating downwards at 9.8 meters per second squared, you would just be floating around. Now, that wouldn't last very long because you'd eventually hit the floor. But the idea is that if the only force on you is gravity, you feel weightless. And what we're used to right now is the chair in this room pushing you up, or the floor pushing me up, and that's what makes me feel like I have this weight, is actually the upward force on you. So they've just removed this upward force. Okay, and this is an orbit kind of drawn to scale. There they are, feeling like they're weightless, but they're just accelerating towards the center at 8.7 meters per second squared. What time is it? We can do an example of this car thing. How fast would you have to drive in order to be weightless? So I've always wondered this. If I'm driving in a car at some V, and here's some radius, when would the wheels of my car just lift off the ground? So what I'm going to do, first step, is I'm going to neglect air resistance. That's kind of important. And then, so I get force diagram. Looks like this. mg, you've got a sub r is downwards. And so this is, I guess, the plus r direction is down. So I just get this sum of the forces in the r direction is equal to m times a sub r. So that's just mg, and that's just mv squared over r. So you just cancel the m's. And you get v squared is equal to gr. So you just get v is the square root of g times r. Square root of 9.8, which we know, times 6,400 times 10 to the 3, 10 to the power 3 meters, you get 7,900 meters per second. And that's that 8 kilometers per second I was talking about. If you drive your car at 8 kilometers per second, you're in low Earth orbit. So another quick top hat question for you. It's a weird one. In low Earth orbit, a satellite is only a few hundred kilometers above the surface. And it goes around the world every hour and a half. Why don't satellites have orbits that might be even less than this? This is sort of a minimum, is 300 kilometers. Nobody ever launches a satellite to be like 100 kilometers or 0 kilometers. So why is this? A, lower than that, they would be subject to Earth's gravitational pull. The satellite would fall down. B, lower than that, they'd be too far from the sun and could not collect enough solar power. A lot of these are solar powered, actually. C, lower than that, they'd be subject to too much air resistance and would fall or burn up. D, lower than that, they would be subject to too much radio interference from the Earth, like radio stations. E, lower than that, they would not be able to communicate with the entire Earth at one time. So one of these reasons is the big one. Make sure your friend knows the answer. Vote it in, and then I think I'll call it quits. Survey says, see what people think, and I'll tell you what I think. Okay, so everybody's subject to the Earth's gravitational pull. It doesn't change much if you just go 300 kilometers up, okay? But if you drive your car at 8 kilometers per second, your car will instantly burst into a ball of flame. In fact, it won't even be flame, it'll be plasma, okay? It'll explode, and you'll be way dead because of air resistance. That's what it's all about, okay? So you got to get above the air. So just before you leave, you position your orbit above the Earth's atmosphere where air resistance is almost totally absent. But even these satellites experience a bit of drag, so they need occasional boosters to speed them up. Next Monday, we'll talk about Chapter 6. I'll also discuss Kepler's laws, which is a bit of part of your reading for Chapter 5. That's about it. Have a great weekend.